Hello. Today I want to cover part 5 of my series on essential theorems for harmonic astrology. So give me a minute to share my screen and we can get started. Take just a few seconds to get everything set here. I've got to hide some panels so I can see what I'm doing. We're almost there. And we're ready. Essential theorems for harmonic astrology, part 5, the number of inharmonic angles. At first glance, when one is finding a particular harmonic chart, the end result often seems completely random, but nothing could be further from the truth. Instead, there is a very precise mathematical structure to harmonics, as the next few theorems will show. The first of these theorems formally proves that for any natural number n, there are exactly n harmonic angles. Okay, theorem 4. Let n be a natural number, and let theta sub n equal to 360 degrees over n modulo 360 be the root n harmonic angle. Then there are exactly n harmonic angles, and they are equal to theta sub n, comma 2 times theta sub n, 3 times theta sub n, so on and so forth, until we get to n times theta sub n, and each of those is evaluated. This last one, evaluated modulo 360 degrees, is equal to 0 degrees. And that is because if theta sub n is 360 degrees over n, multiply this by n, and over n cancels, and 360 degrees modulo 360 leaves you a remainder of 0. So you get 0 degrees. Okay, proof. Now, n equal 1 is often just sort of a special case. So let's see what happens in this case. If n equal 1, then theta sub 1 is equal to 360 degrees over 1 modulo 360 degrees, and that is going to be equal to 0. Okay? And if you multiply theta sub 1 by any other natural number, you just get back 0. So that is the only one harmonic angle we have. Now suppose that n is greater than 1. Then theta sub n is equal to 360 degrees over n modulo 360 degrees, but that's just going to be equal to 360 degrees over n. Why? Well, if n's bigger than 1, 360 divided by n is going to be less than 360. So this expression is actually the remainder you get when you evaluate this modulo 360 degrees. Okay, and theta sub n, 2 times theta sub n, all the way out to n minus 1 times theta sub n. They're all greater than 0 degrees and less than 360 degrees. Why are they less than 360 degrees? Well, because whether you're looking at 1 times this, 2 times this, 3 times it, or n minus 1 times this, let's say we go out to n minus 1, well, the angle theta sub n, that is 360 degrees over n. If you multiply that by n minus 1 over n is just a fraction that is less than 1, so you wind up with just a fraction of 360 degrees, something less than 360 degrees. Okay, additionally, n times theta sub n modulo 360 degrees, that's n times this expression. You can cancel out the n's. That leaves you with 360 degrees modulo 360 degrees, which will be equal to 0 degrees. Now, beyond n, if we look at some natural number larger than n, notice that if I take, for instance, n plus 1 times theta sub n modulo 360 degrees, that's going to be n plus 1 in parentheses times 360 degrees over n. If you multiply each term here by 360 over n, you can cancel out this n, and you wind up with 360 degrees plus 360 degrees over n, modulo 360 degrees. This is equal to 360 degrees plus theta sub n, right? Because this thing here is equal to theta sub n. And you evaluate that modulo 360 degrees, but that reduces to just theta sub n modulo 360 degrees. Why? Well, it's because when you divide 360 degrees by 360, you get a remainder of 0, right? This term contributes nothing to the end result. So we're just left with theta sub n times modulo 360 degrees, but since theta sub n, that's this thing here, since 360 degrees over n is less than 360, this just comes out equal to 360 degrees over n, which is the same as theta sub n. So this reduces to theta sub n. So hence, in other words, once we reach n plus 1, we start over with theta sub n. And from this point on, we simply repeat the previous values for harmonic angles as we continue multiplying by larger natural numbers. Therefore, for any natural number n, the n harmonic contains exactly n harmonic angles that can be listed as theta sub n, 2 times theta sub n, 3 times theta sub n, up to n minus 1 times theta sub n. And then the next harmonic angle is n times this, reduced modulo 360 degrees, and that comes out equal to 0 degrees. Okay. Now, as an example of Theorem 4, the root 6 harmonic angle is 60 degrees. That's 360 over 6. And the six harmonic angles, which I denote by h sub 6, it's this set of angles. This is the natural order they occur in. 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and then when you get back to 360 degrees, that's equivalent to 0 degrees. Similarly, the root 5 harmonic is 72 degrees, 360 degrees divided by 5, and the five harmonic angles are 8 sub 5 equal to 72 degrees, 144 degrees, 216 degrees, 288 degrees, and then the last one is 0 degrees. Again, this is the natural order to put these in. You start with the root harmonic angle, and you'll end up with 0 degrees if you're looking at natural number harmonics. Okay, next I present a perhaps obvious but important corollary to Theorem 4. So this corollary says if theta is an n-harmonic angle, then any natural number multiple k of theta reduced modulo 360 degrees is also one of the n-harmonic angles, theta sub n, 2 times theta sub n, all the way out to n minus 1 times theta sub n, and then 0 degrees, where theta sub n is 360 degrees over n. Okay, to prove this, let's assume that theta is an n-harmonic angle. Then, by Theorem 4, theta is one of these angles, where theta sub n is defined this way. Now, if theta equals 0 degrees, then it is trivial that k times theta modulo 360 degrees equals 0 degrees modulo 360 degrees is just equal to 0 degrees, which will be an n-harmonic angle for any harmonic n, actually. On the other hand, if theta is not equal to 0 degrees, then k times theta modulo 360 degrees is equal to k times m times theta sub n modulo 360 degrees, where m is a natural number such that 1 is less than or equal to m, strictly less than n minus 1. Okay? So, what we're doing here is, let's see, we have theta is going to be a harmonic angle, and that means it's going to be some natural number times theta sub n reduced modulo 360 degrees. If I choose m so that let's see, it's in this range, then we're going to have that this m times theta sub n comes out equal to, let's see, something less than 360 degrees. Okay, so we can just do k times this harmonic angle, and that is going to do it for us. So in the case, if I had n here, then n times theta sub n, that would come out to 360 degrees. That reduces to 0 degrees. And actually, that puts us back in this case here, saying theta equal 360 degrees. Well, that is simply what 360 degrees modulo 360 reduces to. Okay, so this basically takes care of that case separately, and this is all the other cases. Okay, well, what does this mean? This also means that k times theta modulo 360 degrees, it's k times n times theta sub n modulo 360 degrees. I could just write that as km times theta sub n, in parentheses, modulo 360 degrees. But this is, by definition, an n-harmonic angle. And so it must also equal one of these angles where theta sub n is this. And that basically just completes the proof. We showed that if theta is an n-harmonic angle, we take any natural number, multiple k of theta, reduce that modulo 360. We just get back one of these existing n-harmonic angles. Okay. Now, the practical importance of this corollary is that any natural number multiple of an n-harmonic angle, when reduced 360 degrees, is also an n-harmonic angle. Okay, so as you multiply these n-harmonic angles by other natural numbers, and then reduce the result modulo 360 degrees, you don't get just anything. You always get back another n-harmonic angle. Okay, recall now that for a natural number, frequently denote our collection of n-harmonic angles by the ordered set h sub n equal to this. I put it down in that order, beginning with the root n-harmonic angle and ending with 0 degrees. Thus, h sub 1 is 0 degrees, h sub 2 is 108 degrees, comma 0 degrees. h sub 3 is 120 degrees, comma 240 degrees, comma 0 degrees. And h sub 4 is equal to this. Furthermore, if n is greater than 2, then a regular polygon will be generated if I plot our harmonic angles around a zodiac wheel and connect these angles by straight lines in the order that they occur in h sub n. And let's see, a regular polygon, that means that all the sides have the same length. Okay. Below are the corresponding graphs for h sub 3, h sub 4, and h sub 12. And in each instance, the root n-harmonic angle is shown by a blue line. So starting at 0 degrees Aries for the 3 harmonic, this first angle is 120 degrees, followed by 140 degrees, and then we get back to 0 degrees. For h sub 4, we begin with our root harmonic angle of 9 degrees, then go to 180, 270, and back to 0 degrees. And for h sub 12, our root harmonic angle is going to be 30 degrees, and we just go around in 12 increments of 30 degrees, and eventually we get back to 0 degrees. Okay, that is going to be it, so I'll stop sharing. And I'm back. So, I hope you found that presentation interesting, enjoyed it, and I hope you join me for the next one. And for now, I'll just say so long and be well.